The important thing in science is not so much to obtain new facts as to discover new ways of thinking about them. William Bragg. Familiar things happen and mankind does not bother about them. It requires a very unusual mind to undertake the analysis of the obvious. Alfred North Whitehead. Every scientific truth goes through three states. First, people say it conflicts with the Bible. Next, they say it has been discovered before. Lastly, they say they always believed it. Louis Agassiz. People were making estimates about the properties of atoms. They were still crude in the late 1800s, but they seem to be object with a definite size. That size was tiny. In the metric system, it's a 10 to minus 10th power meters. It's a little ball about 10 to minus 10th power meters, and it didn't seem to matter which element you are looking at. They were all roughly the same size. All atoms are objects. They have different masses, but they are the same size. This atomic hypothesis becomes a firm science, but it's still not understood in a deep way in this era. People are just describing what's going on without really being able to say why. I want to take a step back from this early development and talk a little bit about the scientific method and the question of how do you know what you know? Why do you believe these things? So, as a metaphor for the developing picture of the atoms, I want to step back in the history and look at the development of another model, one that's a little bit easier for us all to visualize, which is a planetary model. Yes. Go back to the 1500s and people are debating about whether the Earth is at the center of the universe or whether the Sun is at the center or whether there is something else going on. There are various competing ideas. These ideas are backed up by some data. People have been observing the motion of the planets in the night sky, for example, but it's still kind of the weak science. There isn't the idea of the let's work out rigorous mathematical consequences of our ideas, and then check and confirm whether the data agrees. This process really began with the data taken by the Danish astronomer by the name of the Tycho Brahe. I love that name. Yes, so unique, right? Tycho was an amazing character, a very dynamic man. He was in a duel in his youth and lost a part of his nose. Wow. So he had a metal nose. He was favored by the king of Denmark. So this was the first example of the big science. Yes. Here was this guy who developed a research program. He got funding from the government. He got a research laboratory which was on an island off the coast of Denmark, and he took great data. He took excellent data of the motion of the planets through the night sky. Yes. Now, Mr. Brahe had an idea about how the solar system worked, which is by modern standards kind of confused. He saw that the Sun was at the center and that the Earth rotates around it, but then the other planets go around the Earth. It was some complicated system, but he wasn't really interested so much in proving his idea as he was in just collecting the data. This is the first step in the scientific approach, of course. It was his disciple, John Kepler, who really took the next big, important step in the development of science. He had to wait until Tycho died, because Tycho coveted his data. Haha. In those days, you didn't publish or perish. You just held onto your idea. It was valuable. So once Tycho was gone, Johannes Kepler was able to take the data and analyze it. Now, Kepler had this idea, which had been exposed earlier by Copernicus. that the sun is at the middle and all the planets are orbiting around it. Copernicus had thought that the planets were going around in circles, and Kepler said, "Let's ask the data. Let's not be a philosopher about this. Let's be a scientist." So he looked at the data, he made incredibly careful measurements and calculations, and determined that the data implied that the planets are not going around us. They are going around the sun, and they are traveling in ellipses, not in the true circles, but in the slightly squashed circles. Right. This Kepler's brilliant achievement. It's just describing the data accurately. Wow. He's not explaining it. He doesn't tell us why does a planet move in the elliptical orbit. It's just saying it does. Yes, this is what the idea shows. That's very important. When you are first looking at the confusing data, just describe it. However, if you really want to understand something, if you really want to do science, you have to go deeper than that. You need to look at the data and explain it, and based on the some fundamental principles, and the person who did that was Isaac Newton, right? Isaac Newton is a sort of the hero of any course on elementary physics. Isaac Newton was born in the 1600s, and he knew about the data of the Kepler. He knew about the works of the Galileo. He was, in a certain sense, the first real scientist. He, in fact, wrote a book, the Principia, in which he laid out what we call the scientific method. He said we need a hypothesis. They need to have mathematical consequences. We need to be able to make the predictions about what we will see in the laboratory. We need to do experiments to verify those predictions, and then we need to check that the whole story is consistent. Yes. If it's not, then we have to go back and fix up our hypothesis or check our calculations. This method that Isaac Newton developed, he applied in this case to planetary motion. So he's got this idea that planets are moving in the ellipses, and he's trying to understand why. Now, Isaac Newton is famous for sitting in an orchard and seeing an apple fall down and realizing that the force of gravity which pulls the apple down is a universal force, and if the gravity can pull on the apple, how high can it reach? Can it reach up to the moon? This was Isaac Newton's really brilliant insight into how the world works. Why does the moon not fly away from the planet Earth? Why does it stay in orbit? According to the Newton, it's because there is a force of the gravity holding it in. Yes. Why does the planet Earth not fly away from the sun? Because there is a force of gravity attracting us so that we go around in orbit. So now he says, okay, I've got this idea of gravity, and he worked out a formula that tells you quantitatively how gravity depends on the mass of the objects and how far apart they are. Then he applies this. He says, suppose that we have a solar system with a heavy sun and massive planet Earth, what would our motion be? So, in order to do this, he had to develop some mathematics. In fact, he invented calculus. Wow. Very smart guy, Isaac Newton, in my mind, the smartest human being, at least the smartest scientist who ever lived. Yes. He created the science, he invented the calculus, he discovered the laws of motions. The physicist that Isaac Newton discovered and wrote in the Principia has survived. Even today, it is a basis for pretty much all ordinary world science. And physics in particular that we do. Amazing character, he had a brain the size of our planet. Hehehe. He was also not a very nice fellow. Yes, unfortunate. He never married. He was kind of the archetypal nerd. He worked really hard. He had this incredible ability to focus on what he was thinking about. not a nice guy. He had a lot of enemies. I think he was always worried that he might find somebody that was half as smart as he was. Haha. So Isaac Newton has taken Kepler's ideas and started from scratch. At some deeper level, he has said, I believe that there is a universal law of gravity which applies to all objects. By applying this law, he had deduced that planets move in elliptical orbits and that they have the various properties and the period and the radius relationship that Kepler had also observed. Right. Isaac Newton is explaining Kepler's summary of the data. Now we have a much deeper understanding of the planetary motion. It's no longer just a theory. It is now a deep, rigorous mathematical framework, and instead of reproducing the data that was already taken, you can now begin to make predictions. What would happen if we launched our rockets? What would happen if we tried to send people to the moon or to the Mars? We can use Newton's laws and they will tell us exactly how to do that. And of course this has succeeded spectacularly, yes. I think that the scientists were satisfied with the picture of the atom in the late 1800s as a description of the nature. So, going back from Newton and his development of the scientific method to our development of our idea of atoms, people were satisfied with the idea that atoms are real. They are physical objects, little teeny things that bounce around and interact with one another. They can explain an enormous wealth of data about physical properties of materials, chemistry, and from that biology. Yes. But there was still kind of the lack of understanding of the underlying theory. It was like we were at the stage of Kepler describing what was going on, but we didn't yet have our Isaac Newton to explain what is an atom, what is it made of, why does it interact the way it does, why does the periodic table appear as we have seen it in our high school chemistry class in these lovely rows and columns? Why is it that there is a disordering to the atom? In order to develop that idea, we need something more, something beyond the physics of the 16, 17, 1800s. What was missing was a quantum physics and relativity, yes. The transition from the classical physics of the Newtonian era all the way up to the 1800s to what we now call modern physics, which is this idea of how things work when they are really tiny, that the transition had not yet been made. There were some hints out there, and we are going to be talking in the next lecture about what those hints were. That physics was not quite done in the late 1800s. Right. Let me tell you about two of those primary hints. Number one, around the same time that the periodic table was being developed, published, understood, we also were discovering a new phenomenon of the nature: radioactivity. Radioactivity didn't fit in with this scheme of atoms. Very mysterious. Energy just spontaneously being generated and spewing out of some certain unusual material didn't fit in with the classical picture. Yes. So now you can see the gaps. Now you can see the huge hole that things are disconnected each other. Yet consequently you see the result is very in harmony. So these gaps, this hole, implies there is something missing. There is something you can find out, right? That was one clue that we really didn't understand everything about the world. In fact, when you had a radioactivity, you observed this bizarre phenomenon that an atom, like a nitrogen atom, could change. If you bombard it with a radioactivity into a different kind of atom, could convert nitrogen into oxygen. Yes. This goes against all of the idea of the chemistry, which says that the world is made of atoms. Because the atoms should be every individual atoms are the minimum units of the chemistry. That is why what tells here is implying there is a subatomic level of something, right? Subatomic level reaction. That is why the atoms can change into the another one. Right. This goes against all of this idea of the chemistry which says the world is made of atoms. Nitrogen is one kind of atom, oxygen is another kind of atom. They can bounce, they can stick together, but they can't change. They are indivisible and immutable. Remember, atom comes from the word atomo, which means uncuttable. So, radioactivity was a puzzle. Radioactivity was a puzzle. There were other puzzles at the time. For example, when you heat materials up and you look at their glow, this is an easy phenomenon to observe. Look at your oven, it glows red hot, right? If you try to calculate using the law of the classical physics, what's going on? You discover that they don't agree with the data. Ha 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 ha. So, next time, we are going to talk about these conflicts between the classical physics and the experiment that lead us to deeper understanding of what are atoms. What are they made of? What are they really at some deep level? What's the theory? Thank you!